Yeah, so hello everyone. Welcome to the the lab part of the course microelectronic circuits or devices and circuits. Um, this is the analog IC design part of the course, and yeah, so all through for this session or for the next few videos, it would be just on analog IC design. Yeah, so let's just get started. But okay, also okay, what you've mentioned, it's okay. What generally what we're going to be designing for this analog IC. So first we'll be starting with the very basic. That's the common source amplifier. First there'll be a lot of assumptions, being that you've taken this, you've been taught in class the theories and the concepts, so it may not be all basic, all designs that would have to do. So we'll just do the common source. We may not do common gates, and that's the current buffer and the voltage buffer, which is the common drain. And by the way, yeah, this design is biased towards CMOS. So this is analog CMOS design. Yeah, analog IC CMOS design. Or yeah. So yeah, no BJT, and also that's why I just mentioned common source, common gates, and common drain. Yeah, so we may not do the common drain and the common gates, just the common source, the most popular form of amplifier, the most popular basic amplifier, I would say. Then from there we may move to differential amplifier. Yeah, and differential amplifier, also the single stage op amp. Then from there we'll move to multiple stage op amp, or maybe before multiple stage, that's two stage would be fine for a multiple stage, but maybe before multiple stage we may still do cascode amplifier. So the different cascode, maybe folded cascode. We may skip the telescopic cascode. So don't worry, all this would be demonstrated and illustrated very well all through the video, but I'm just giving you like overhead, like information. So let's just get started. I'll be starting with the common source first. Again, analog IC design and bias to CMOS, so analog CMOS design. Okay, so let me just show a picture here. So this is a textbook by Tony Chan, yeah, titled Analog Integrated Circuit Design. I'm just saying the name for reference purpose and for reference, that is this a reference, this a source, so I'm just citing it and just like giving the credit to the source, so not necessarily for you to go maybe check the textbook. I guess the recommended textbook by the course coordinator is already enough, so but I just want to use this to just illustrate and show what the common source amplifier looks like. So this is a common source amplifier. Maybe it's slightly different from what you may have seen before, in sense that this part of the circuit, maybe from what you've done in class, maybe the first part you guys did was the part where this, instead of a transistor here, instead of like this entire PMOS transistors here, just only a single resistor. Maybe that's the right, maybe that's one of the forms of common source you guys did in class. Then perhaps another form was where instead of the resistor you'd have, I wish I can show, okay, let me just come in. Okay, so I was talking about the different forms of common source. So this one way, and as like I was saying, maybe another form you may have seen, it's the form where you have just a resistor here instead, such that the gain will be just with GM. Let's say the resistor value is RD, so it will just be GM RD, right? That's one form. Another form could be this. So now this reference from Owe and Sodini, I think, yeah. So you've seen this. This is another form where this NMOS for, so just we're talking about the NMOS common source amplifier. So you have the NMOS, then instead of a resistor, the resistor like is there for biasing. So now instead of a resistor you have a current source for biasing. So yeah, this is another form where the gain will be GM RO of this transistor parallel ROC of that's the ROC, the output resistance of the current source, you get. So but in reality this is not really realistic. This is ideal because what's a current source like? How can you get the current source in real life? Like maybe really in real life, maybe just like how you may have a voltage source, maybe example is battery, or maybe just any source of EMF. But for current source, it's not really like there is a component that exists really that we call a current source. So most times we would have to design a current source. Maybe for a voltage source it may have already been designed, so for instance maybe battery or any source of EMF, but for current source you may have to design, right? So similarly for analog IC design, the current source have to be designed, and many times we use a transistor to design a current source. So remember, and it's possible because from the IV characteristics of a transistor, at a point in a region the transistor behaves as a current source, and that's the region where it's in saturation, right? So in real life, in practical design, this current source will be replaced by just a single transistor, you get. So we're moving from ideal to practical design, you get. So this can just be replaced by a transistor, and the transistor you'd have to bias it so that it will serve as a current source. So I'll tell you, that's just what we have here. So that's the transistor. Now this is a transistor here that will be serving as a current source, that will be replacing this current source here, right? And transistor you'd have to bias or you have to do some things to it for you to get what you desired. Like, so mostly for you to get the current source behavior out of the transistor, you need to take it to saturation, right? So that's what this other guy is doing here. So it's providing the necessary bias voltage here for the gate of this Q2 transistor, so that this transistor would be in saturation, thereby serving as a current source, you get. And this whole structure here maybe you've now got into the part of the class where this has been taught. Like, so this whole structure here is called the current mirror, right? So current mirror. So but I just deconstructed what the current mirror looks like. So a current mirror, really, we use it for biasing, right? So I just have to start from here. So biasing, you need this, basically a current source. That's what the current mirror is. So this is a current source here as a transistor. This other part of the current mirror helps to provide bias for this. So this structure together, Q3, Q2 together, are called current mirror. Right, so and their purpose here is to give bias to this guy Q1, and yeah, so by giving bias, that means they're serving as current source. So yeah, this again, yeah, we still have the ideal current source here, but it's better than this because we can just do the design, and I mean the physical design. You know, for analog IC design, you do your design, electrical design and simulations. Then from there you move to layout, and after everything do your post layout simulation, then you tape out, right? This, even if there's still an ideal current source here, it's better than having just ideal current source here, because if the current source was to be here, like when the current source was here, the ideal current source was here, it's parts and parcel of the old amplifier, right? The common source amplifier, the common source amplifier that will be taped out and will be fabricated as a chip, right? That's not good, because if you want to say, okay, you want to get a current source externally to do that, it's not good, because this current source should be parts. This current source, whenever a current source is here for a common source amplifier, a current source is here, it becomes part and parcel of it, and should also be sent for fabrication. So this ideal current source, you know it's ideal. You can't actually get a current source and just place it there and want to. So a way to realize this current source is by using this using transistor. What is fabricatable, right? So transistor is fabricatable, so by using a transistor. So now we've removed that current source from here, so we would not have any issue because everything would be fabricatable. But now the current source being here is better, because now everything, like I said, everything like this Q1, Q2, Q3, that what will be fabricated. So this is still okay to be external, because this does not have to be fabricated alongside. But when the current source was here, where Q2 was before, and where QT currently is, it needs to be fabricated. But then ideal current source is not fabricatable. Like ideal, like current source, just like how you have a voltage source, maybe battery, you don't do that when you want to go and like fabricate. So you need to use a component to realize this, and those components must also be fabricatable. So that's how we use a transistor. So now we are fine just fabricating Q1, Q2, Q3, then we just use this externally. I hope that explanation is clear. If it's not clear, you can just let me know, then I'll do a better explanation on that. So this is a more practical current common source amplifier. What we have here, this is more practical than this. This does not exist. Take it, just if you like, just yeah, this can be argued whether current source exists or not, but current source, if you like, you can just take it to be an abstraction, right? There's no current source in itself, maybe just like how you may have a voltage source in itself, but you can use something to realize the current source. So this is just an ideal common source amplifier. So what will make it practical is if you can, if you can find things around to realize this. So to make it practical is by replacing it with what you have already on ground that is realistic. So, and again, that's your transistor. So that's why this is more realistic than the other. So that's why this is how our common source amplifier would be. So this is what we want to design. We'll be doing our design and simulation on this. So we're going to be doing design, simulation. That's design, we're going to do our calculation on this, simulate it with spice to verify that everything is good, then move to doing the layouts. Yeah, we're going to do the layout, everything, then also the post layout simulation of it. So yeah, that's how we're going to be moving. Yeah, so that being said, so I'll just be moving to the design and simulation. So remember, we're going to be using a scheme, open source IC design tools. So for me here, I have a scheme and I have the open PDK, that's the GF180 PDK. That's what I'm going to be using. But for you guys, I think you have the Skywater installed, right? So you'd be using the Skywater. Yeah, but we're all good. I would where it's different for Skywater, I will let you guys know. So yeah, I think that will be all for this video. So I'll just, for the next video, I'll just get started with the design and simulation. Okay, see you next video. Yeah.